So good morning, everyone, and thanks to the organizer for giving me the opportunity to talk about my work here. So I'll be basically talking about some classical string solution where the string is propagating in a black hole background. And you can think of this as a string as a one-dimensional object which is propagating in some space, and that space is a black hole. And and I'm looking for its trajectory. Uh, so now another point is that we believe that there is a bulk boundary correspondence, like bulk theory, I mean some theory of gravity. And in the boundary of the space, there is a quantum field theory, and there is a duality between them. So if I think about this string propagating in a black hole is a bulk problem, then these solutions would have some field theoretic description. So I also talk about that. So this is a plan of my talk. So I'll first discuss the connection between the black hole, where the string is propagating, to some other spacetime is called ADS3, and which is simpler than this black hole, and where the string solution is better understood. So I'll use this connection to construct the string solution in the black hole scenario. And then once we have understood the connection, then I will tell you how to construct the string solution in this black hole background. Then the third would be the field theoretic description of the solution. And fourth, if I get time, I will explain this plane wave spacetime, which is basically a solution of wave-like solution of Einstein equation. And in some limit, you can get this spacetime from any given spacetime. And from ADS3 and BTG, both lead to same plane wave spacetime structure, and I'll tell you the reason. Okay, so let's consider a flat space R2, 2, which is characterized by 4 coordinates, x0, x1, x2, and x3. And the metric of this space is given by equation 1, and you can use it to compute the distance between 2 points in that space. So now, given this space, I am interested in a particular hypersurface in this space, which is given by equation 2. So it's something like you can think of like when you study sphere, and which is given by the equation x square plus y square plus z equals r square in R3, which is characterized by coordinate x, y, z. But here in this case, it will be hyperboloid. Now, given this hypersurface, the next thing is to define the coordinate system. Now, here comes the interesting fact that if you use coordinate system 1, so you can use different coordinate system to study this hypersurface. If you use a particular coordinate system 1, you will get a space which is called some 3-dimensional ADS space. And if you use another coordinate system 2, you will get a 3-dimensional black hole, which is called BTG. So one case you have a black hole, in other case you have a non-black hole spacetime, there is no black hole, and they are related by a coordinate transformation. So that basically means given any quantity, any physical object in this space, let's say ADS, you just have to use the coordinate transformation to get the physical object in the other spacetime. So for example, I can take a ballistic particle of mass m sitting at the origin of ADS. Okay, so you can use the coordinate transformation, and you can show that corresponds to a particle which is falling into the black hole. And of course, you have to identify some parameter in the both cases, and that will be you can show from the coordinate transformation. And this space-time has some symmetry, and we know that for symmetry lead to some conservation, so you can compute many conserved charges, and you can show that using the coordinate transformation that the conserved charges for the ADS and BTG, they're related by a boost. So 1, 2 boost. And also you can show that the norm of these charges, they remain invariant. Okay, so this is the connection of these two spaces. Now I want to show how to construct the classical string solution in this black hole background. So consider these two spaces, ADS3 cross M7 and BTG cross M7, and this M7 is some 7-dimensional space. Now consider this, because I took this M7 because we need 10 dimension to study string theory. Now suppose a string is propagating in this space, okay? And consider a particular solution where this string is behaving like a point-like object in ADS and a BTG part of the space, and they are allowed to do different kind of motion, not point-like in M7, such that they satisfy called the Virasoro constraint. it is some condition that appear in string theory, and any valid solution of string need to satisfy this condition. Now, so previously I've shown you that norm of the charge driven constant, you can show using that relation that the Virasoro condition for both the cases actually are satisfied. And then you can say that classical string sitting at the origin of ADS, if I give you that solution, you can just use the coordinate transformation and compute the infalling classical string which is falling into the black hole. Okay. Yeah, so now there are many classical solutions one can study, like a geodesic solution, circular string, Jan Magnon. So these are basically geodesic solution means where the string is point like in a whole space. So ADS3 or BTJ and even M7, they are point like in whole space. And other two circular string or Jan Magnon, they are point like only in the BTG or ADS part. And for the M7 part, they are allowed to take different kind of motion, like there could be other coordinate dependency. Okay, so this is the way you can construct the classical string solution. Now I want to talk about what this solution mean in the field theory description. Okay, so I mentioned before that there is a duality between bulk and boundary theory. So bulk theory basically means there is a theory of gravity, and in the boundary there is a quantum field theory. And for an example, you can consider ADS safety correspondence, where in the bulk you have a ADS spacetime and you study the gravity theory around the space, and the space has a boundary, and there is some special kind of quantum field theory lives on, which is called conformal field theory, and there is a correspondence between them. So for an example, you can consider that, you can consider just empty ADS3, no gravity fluctuation, no matter, nothing, just empty ADS, and that will correspond to some vacuum state in the boundary field theory. And for this case, this is ADS3, so the boundary would be a two-dimension. So the field theory would be a two-dimensional quantum field theory, and this quantum field has a special structure, that's why we call it CFT, so conformal field theory. So then if you put a point particle at the center of ADS3, then it will backreact with the geometry and it will deform the geometry. It's called a conical defect geometry, and for this 3D case you can exactly compute the backreaction, and it's called a conical defect geometry, and that would correspond to some excited state in the CFT, and that state you can create by acting a primary operator on the vacuum, and that dimension of the primary operator would be proportional to mass of the particle. So in general, you can take ADS spacetime, put any like metric fluctuation, you can put many matters on it. Then in the CFT, that will be some excited state, and that will contain many such dual operator. Like for matter field, you will have some different kind of operator. So that's the duality between this. Now I'll talk about for the BTG black hole. So for the BTG black hole, the dual field theory would be a finite temperature CFT, and that temperature of the field theory will be fixed by the horizon of the black hole. Now, the duality for the black hole case would be if you consider the empty BTG black hole, and that would be the vacuum state in the thermal CFT. And now if you put a point particle, or let's say if you put a particle which is infalling into the BTG black hole, then the deformed geometry would correspond to some time-dependent state in the thermal CFT. And that is very expected because the particle is infalling, so it has a non-trivial dynamics. So the CFT state should be also time-dependent. And that is expressed in terms of some density matrices, and it's called Cohen state. And so this Cohen state has a very interesting properties. So this looks like a pulse at time equals to 0. Then at later time, it's split into two pulses which propagate at the speed of light. You can see the peak of the pulse actually, so at t equals to 3, you can see the peak of the pulse exactly lie on like at x equals to 3. So you can see they are propagating at the speed of light. Now for higher D black hole, so for 3D case, you can exactly compute the back reaction using the Einstein equation. But for ADS case, then you just use the coordinate transformation to compute the back-reacted geometry for the black hole case. But for higher dimensional ADS case, this such coordinate transformation doesn't exist. And if you want to put in the, if you want to solve the Einstein equation, become very complicated. So you cannot solve it. So for higher dimensional case, we just don't know what is the backdirected geometry. And so this is an open problem. Okay, so next I want to explain the plane wave limit of ADS and BTG. So consider a wave-like solution of Einstein equation. So this is given by this is almost like a flat space, but there is extra component which is d. So there u and v is a light cone coordinate. And now this space has very interesting properties. This is interesting for many ways. First is admit some covariantly constant null killing vector. Then you can show that if this fu is satisfy the Laplace equation, then all the curvature invariant just vanishes for this spacetime. So this is very interesting as a background of string theory. But is first this introduced by Roger Penrose. Okay, so first Roger Penrose introduced a method called Penrose limit, and using this method you can generate plane wave geometry like such geometry out of any given spacetime. And the procedure is basically you take a null geodesic in the space, then you focus on the neighborhood of that geodesic, and then you is basically zoom the surface in around the null geodesic, and you end up this plane wave geometry. So now I will take two particular spacetime, ADST and M7, and this BTG cross M7. Now consider a null geodesic in ADS3 cross M7. Now from just ADS point of view, you can see this null geodesic as a massive geodesic, because let's say you consider this observer sitting at the origin of ADS3 and rotating along one of the circle of M7 with angular momentum j. So then you can, just from ADS3, it looks like a geodesic of a massive particle, and this mass would be equal to j of the particle, angular moment of the particle. Similarly, from the BTG case, if you take BTG cross M7, you can the null geodesic in the whole space is looks like infalling massive geodesic. So now we have already argued that ADS and BTG are locally the same because they are later ways of coordinate transformation. Also, using the coordinate transformation, we have shown that the static particle at ADS3 can be mapped to infalling observer into the BTG black hole. So if we take the plane wave limit around those null geodesic, we should expect that they should lead to the same plane wave geometry. And this can be verified by explicit calculation. Yeah, that's all.
Thank you, Rahul. Questions?
Hi, thanks. Is this working? Yeah. So you mentioned that locally ADS3 and BTZ black hole are the same.
Yes.
So are we talking about some specific patch or like more global?
So locally are the same. Globally mean, so here I'm talking about the Rindler BTG. It's called, like, if you use the coordinate transformation, you can see this metric starting from ADS metric. If you use the coordinate transformation, you will exactly get the BTG metric. But only one difference is that there will be one coordinate which will be which can take value minus ∞ to plus infinity. But for the BTG black hole, you need that to be a periodic. So you have to make it periodic. That's why then you will get the BTG black hole. So that's why people often say the BTG black hole is an orbifold of ADS, and this orbifold actually comes when you periodify, make the coordinate periodic. So globally they are not same, but locally basically they are same.
The space in which strings propagate for your case, which is ADS cross M7 or BTG cross M7. So what is why 7 here? Where does that?
Because I said we need a 10-dimensional space for the consistent of string theory. So that's why it's some 7-dimensional space. It could be S3 cross S3 cross S1, could be S3 cross T4 or K3.
While defining solutions of string, you said that it behaves like a point geodesic.
Yes.
Yeah. Could you explain what do you mean?
So usually string is a 1D object. So if it's propagated, you will expect that the trajectory would be a seat, not a line, right? But you can think of that string has a center of mass. So when I say it's a point-like object, it's behaving like a point-like, so basically I'm considering the motion of its center of mass. That would be kind of a geodesic. So here, if I'm ignoring all the other dependency of the code, like this extension.
Any other question? Okay, I have one small question. Can you go back to your slides?
Which one?
Where you have drawn the ADS thing.
ADS?
Like
okay.
You were showing. Yeah.
This one, right?
What is this diagram? Are these hyperboloids or what?
So this is actually the, okay, so this is a cylinder.
No, but on the top you have some.
No, that
pattern.
is just nothing.
Nothing.
This is nothing. This is some picture.
Okay. So, thank you, Rahul. Let's come to the speaker.